Are there any green stars? Yes, there are. Can we see a green star? We may never see a green star without a filter. Hello and welcome to the discourse. It is said that the sunlight contains all the colors. It is true and can be proved by the dispersion of sun rays when sun rays split into a rainbow spectrum as it passes through the tiny water droplet present in the atmosphere, resulting in a continuous spectrum of light appearing in the sky. However, the spectrum of sun rays not only encompasses the visible range, it goes to the ultraviolet region and passes through the infrared region. In fact, our sun and all other stars can be compared to nearly perfect black bodies because the stars emit EM radiation across most of the electromagnetic spectrum. What is a black body? When electromagnetic radiation falls on a body, it absorbs some radiation, reflects some of it, while some radiation transmits its energy to the body. German physicist Gustav Kirchhoff suggested the idea of an idealized body in 1860 that can completely absorb all incident rays of all wavelengths for all angles of incidence, and neither reflect nor transmit any, that is, no energy transmitted through the body. Since such a body absorbs all the electromagnetic rays, it is a perfect absorber. Kirchhoff named such a theoretical body as a perfect black body. Despite the name, black bodies are not actually black as they radiate energy as well. The amount and type of electromagnetic radiation they emit are directly related to their temperature and not affected by the material of the object. Thus, black body radiation is essentially a thermal radiation. Being a perfect absorber, the black body is an ideal emitter too, with an emissivity of E is equal to 1. That is, at thermal equilibrium or at a constant temperature for all wavelengths, a black body emits as much or more thermal radiative energy as any other body at the same temperature. In addition, the energy is radiated isotropically, independent of direction. That is, the black body radiates the same intensity of radiation in all directions. The spectrum of emission of such a body is known as the black body radiation. In contrast, any such hypothetical body that absorbs none of the radiation falling on it and reflects all of it is termed a white body that reflects all incident rays completely and uniformly in all directions. All real materials have an emissivity lesser than 1. However, some bodies can be compared with an ideal black body because their emissivity reaches very near to 1. Our Earth is considered a nearly black body. Earth is not a perfect black body, but it behaves as a black body because it radiates almost all amount of heat it absorbs and maintains the heat budget. Why is Sun a black body? Our Sun and other stars of the universe are also considered nearly perfect black bodies. Sun emits radiation of all wavelengths from radio waves to gamma rays, and its spectrum closely matches the Planck curve. However, the cause of the Sun's energy is nuclear fusion. The Sun initially generates non-thermal radiation, of course, in the course of nuclear fusion. Photons of wavelength energies appropriate to the nuclear reaction, not to the temperature of the hydrogen being fused, are generated. However, the core of the Sun, where nucleosynthesis takes place, is far from transparent. The Sun's core is extremely dense. The Sun's core is about 16 million degrees hot and has a density of around 160,000 kg meter per cube. This is over 20 times denser than the dense metal iron, which has a density of only 7,000 kg meter per cube. However, the pressure at the Sun's core is also extreme, which keeps the hydrogen in gaseous form. This extreme density causes frequent collisions between the photons produced at the core through fusion and the gaseous hydrogen atoms and ions. The density of the Sun changes from the core to the surface. The photons takes maximum time struggling to come out from the core due to continuous collisions which cause the random walk problem. As the photons move towards the surface or the photosphere of the Sun, their velocity increases. It is estimated that the energetic photons produced during the fusion at the Sun's core take between 10,000 to 170,000 years to reach the Sun's photosphere or the outer surface. The photosphere is the outer sphere of the sun that we can see because inside it the sun is opaque. During this huge period, the photons have enough time to attain thermal equilibrium, and when they leave the photosphere at the speed of light to reach the earth and space, they behave like black body radiation. The sun's rays are isotropic, that is, the intensity of sun rays is the same in all directions because the temperature at the sun's surface remains almost the same around 5600 degrees centigrade. Since the original source of these photons is fusion, which continues to face changes in them, the sun offers a continuous spectrum of all possible EM radiation from gamma rays to AM waves. However, the sun doesn't emit an equal amount of all these different types of radiation. The black body spectrum of stars describes the amount of light radiation in the visible range at each wavelength and depends on the temperature. What is the color of our sun? Stars emit light over a whole range of wavelengths or colors. The wavelength where the amount of light peaks determines the color we see, although they will also emit plenty of light at other wavelengths. In general, cooler stars appear red and hotter stars appear bluish. Our sun emits a major portion of its photons in the visible region with a wavelength resembling to that of green color. Hence, the sun must appear green. However, our sun does not appear green. This happens because while the sun's radiation peaks at green, it actually produces almost as much red and blue light. The same is the case with all the G-type medium-sized stars. When we see the sun at sunrise or sunset, when it is low in the sky, it may appear yellow, orange or red. But that is only because its short wavelength colors, green, blue, violet, are scattered out by the Earth's atmosphere. Much like small waves are dispersed by big rocks along the shore. Hence, only the reds, yellows and oranges get through the thick atmosphere to our eyes. When the sun is high in the sky, the shorter waves, primarily the blue, strike air molecules in the upper atmosphere and bounce around and scatter, hence explaining why the sky looks blue. Enough of blue light is scattered out in Earth's atmosphere to cause the sun to appear slightly yellow. However, if the sun is observed from the space station outside of the Earth's atmosphere, it appears white. This happens because while the sun peaks at green, it also emits a lot of rays with wavelengths corresponding to red and blue color. The mixture appears white to our eyes. Similarly, the hottest stars only appear bluish but not violet, as even intense violet light is joined by many other colors. The biology of our eyes also plays the trick. Our eyes have light-sensitive cells in them called rods and cones. Rods are the brightness detectors and are blind to color. Our eyes have three kinds of cones that help us see color: red cones, blue cones and green cones. When light hits them, each gets triggered by a different amount. Red light, say from a strawberry, really triggers the red cone, but the blue and green cones stay rather calm. Most objects don't emit or reflect one color, so the cones are triggered by varying amounts. An orange, for example, triggers the red cones to go about twice as much as the green cones, but leaves the blue ones alone. When the brain receives the signal from the three cones, it says this must be an orange object. If the green cones see just as much light as the red, with the blue ones not seeing anything, we interpret that as yellow. Since the blue color is scattered by the atmosphere, our eyes see the green and the red color of the sun during the noon and it appears yellow. This means that irrespective of where you are, within the Earth's atmosphere or outside in space, a star will appear green only if it almost exclusively emits green light, which is impossible for a star due to its black body radiation. However, if you use the proper filter on a clear day, the sun will appear green. This color diagram shows what's known as chromaticity space, with the curved edges of the diagram showcasing how light of specific wavelengths in nanometers appears to human eyes, while the black curve in the middle corresponds to the color produced at various temperatures in Kelvin. Note that the black curve corresponds to allowable star colors. It does not mean that there is no source of cosmic green light that we can observe. We frequently observe cosmic green light. The commonly green aurora on Earth are an accessible example. Comet comas frequently appear green too, and there are green peace galaxies in the space. There are some nebulas, the enormous gas clouds that clearly shine an eerie green. They appear green because they do not emit light like a star. Instead, superheated gas loses electrons, becoming ionized. When those electrons recombine with those ions, they emit light at specific wavelengths. A gas cloud appears green when the oxygen present in it is doubly ionized at extreme temperatures of 50,000 Kelvin or above. A gas cloud nearing a massive cosmic outburst like that of quasars or cataclysmic events goes through such extreme temperatures and hence it emits greenish light. So this is it for today. We will continue to discuss science, physics and cosmology. Please stay connected with the discourse. Thanks and regards.